The example 1 which we will now take to start with is a 2-degree freedom system model, a spring mass system. We will take up this as an example. Let us say my example problem is 2-degree freedom system model which has mass m1 and m2. The degrees of freedom are marked here as x1 and x2. The model does not have damping, but it has restoring force K1 and K2. So, I want first to draw the free body diagram to write the equations of motion. So, listen carefully, how do we draw the free body diagram and then derive the equations of motion using Newton's method. There are 5 methods based on which you can derive equations of motion: simple harmonic method, Newton's method, energy method, Rayleigh method, and using D'Alembert's principle. So, the details of these methods individually can be examined and studied and understood from the reference textbooks and NPTEL courses which I cited in the previous slides. We will not talk about those methods in detail in this particular course. We will simply take one simple easy method which is Newton's force method and try to derive the equations of motion. Okay? So, now this is my mass m1. When the mass is allowed to pull downwards by this x1, let us say the force, okay, the mass will be restored by the spring. So, I give a unit force and it will be restored by stiffness and displacement, because you know stiffness is actually force by displacement. If I multiply stiffness with displacement, I will get the force. So, when the mass m1 is tried to move by unit force at the first degree of freedom x1, K1 spring will restore the mass. At the same time, the K2 spring will be compressed and will apply a force in the opposite direction, because K2 will be compressed now, it will oppose this motion, and that will be equal to the stiffness of that spring multiplied by the point where you are measuring the displacement and the point where the spring is connected. It is very clear, please understand here. X1 is the point where you are measuring the displacement or the force given, and x2 is the point where the spring K2 is connected. K2 is connected between x1 and x2. So, I say x1 x2. The direction of K2 is simple, m1 is trying to pull down, K2 will oppose m1. So, opposition, m1 tries to move down, K1 is trying to pull it up. So, the direction, the force value, the direction and the force value are very clear in this particular figure. Let us do this similarly for mass m2. So, same logic, mass m2, I apply unit force along x2, when I apply that, the spring K2 will try to oppose that, and that is going to be equal to K2 multiplied by the point where the unit force is applied minus the point where the spring is connected. It is very simple. K2 is connected between x2 and x1, you can see that x2 and x1, and first coordinate will be where you are measuring the force, second is where you are connecting this force. Okay. The direction is very simple, mass m2 is pulled down, therefore, K2 will try to pull it up. I do not think any confusion is there in marking the arrow directions of the stiffness of the springs, marking the arrow direction of the unit force, and therefore, now this is my free body diagram. Now, we are ready to write equation of motion using Newton's law. So, I want to write equation of motion. So, let us say first degree. I am writing a force balance equation. We know that force is equal to mass into acceleration. So, m1 x1 double dot will be acting down, that is the acceleration force given by the x 1 double dot, which is actually the derivative of displacement x 1, which will be actually equal to minus k 1 x 1, negative sign because m 1 x 1 double dot is acting in the downward direction, whereas k 1 x 1 is a restoring force in the opposite direction, therefore, minus sign. Similarly, again a minus sign for k 2, which is x 1 minus x 2. So, let us say m 1 x 1 double dot is minus k 1 x 1 minus k 2 x 1 plus k 2 x 2, which is minus x 1 of k 1 plus k 2 plus x 2 of k 2. Rearranging m 1 x 1 double dot plus k 1 plus k 2 of x 1 minus k 2 of x 2 is 0. That is my first equation of motion. How can I say it is first equation of motion? Because in the first equation of motion the coordinates are x 1 and x 2, okay, they are connecting, because I have applied unit force which is having acceleration in the first degree of freedom. Now, let us do for the second degree of freedom. So, look at this figure now. So, m 2 x 2 double dot is equal to minus of k 2 of x 2 minus x 1, which is minus k 2 x 2 plus k 2 x 1. So, rearranging m 2 x 2 double dot minus k 2 x 1 plus k 2 x 2 is 0, second equation. So, I have written the equations of motion. I can write also them in a matrix form, because computer methods require more simple method of representing these equations. Let us say equation 1 and 2 will be represented in matrix form. Let me write the equations first. M 1 x 1 double dot plus k 1 plus k 2 of x 1 minus k 2 of x 2 is 0, that is the first equation. The second equation is m 2 x 2 double dot minus k 2 x 1 plus k 2 x 2 is 0. I want to represent this in matrix form. So, I can say now m 1 0 0 m 2 of x 1 double dot x 2 double dot plus k 1 plus k 2 minus k 2 minus k 2 k 2. This is stiffness matrix, x 1 x 2 is 0. One can read this first row m 1 x 1 double dot plus, that is this term, k 1 plus k 2 of x 1, this term, minus k 2 of x 2 is 0. So, I get the equation. Similarly, the second row m 2 x 2 double dot minus k 2 x 1 plus k 2 x 2 is 0. So, the equations are now converted to a matrix form. This matrix is called mass matrix. This is a displacement vector, this is stiffness matrix, this is displacement vector, acceleration vector. So, I say this is going to be E. So, inertia force, restoring force, excitation force. Of course, this is 0 in this case. We have to set it to 0, we have to set it to 0 to estimate the fundamental characteristics of the dynamic system. That is why they are otherwise called free vibration characteristics. They are also called natural frequencies, because under no excitation force these frequencies are demonstrated by the system. That is why they call natural frequencies and mode shapes. So, writing equation of motion gives me two inputs. One, the mass matrix is an input for my analysis. The stiffness matrix is also an input for my analysis. Okay. For my computer methods, I should be able to derive the mass and stiffness matrix and give them as an input. Okay. Once I have this input, I want to estimate the frequency and mode shape. So, step number 2, to determine the natural frequency. As I said, we are doing this problem by hand. So, we will do this solution by classical eigensolver method, then we will introduce you to the computer methods and solve the same problem very easily using a computer program. So, equation of motion can be easily written for this problem. So, now to estimate the natural frequency, we will take slightly a complicated problem. So, we are taking a frame of single bay 2-story. The mass is lumped at both the locations. I call this as m and this as 2m, and this is my degree of freedom x1 of t and x2 of t. And the frame has dimensions as given in the screen now. The height of the frame is h and h. So, let us know that the mass matrix in simple terms very quickly can be identified from this, which is going to be 2m 0 0 m. Okay. I am not deriving the equation of motion. I believe that you understood from the previous slide how equation of motion can be easily derived by using force balance method suggested by Newton by drawing free body diagram. So, I believe that you know that. So, this is an equivalent system now. The equivalent system is mass, spring, mass, spring and so on. So, the stiffness matrix when you do the equation of motion will be 3 minus 1 minus 1 1 with the multiplier of k, where k is 24 E I by h cube, because we are looking for a bending stiffness. Okay. So, I have the mass matrix now, I have the stiffness matrix now, which I also derived from the first principles by writing equation of motion for a simple problem. Okay. For this problem similarly apply the same technique. This is a small homework given to you. You will be able to arrive the mass and stiffness matrix as shown on the screen now. So, let us find the natural frequency for this system. Okay. So, it is very simple. Find the determinant of k minus omega square m and set it to 0. So, let us do that. Determinant of, you know, k matrix is 3k minus k minus k k and m matrix 2m 0 0 m. Okay. So, I am writing it here 3k minus omega square 2m, that is k minus omega square m minus k k minus omega square m. Okay. I set this determinant to 0. So, doing that, expanding, I get 3k minus omega square 2m into k minus omega square m minus k square is 0. Again expanding, 3 k minus 3 k square, 3 m k omega square minus 2 omega square m k plus 2 omega 4 m square minus k square is 0. So, rewriting 2 m square of omega 4 minus 3 plus 2, that is 5 m k of omega square plus 2 k square is 0. Let omega square be x. So, the equation now becomes 2 m square x square minus 5 k m x plus 2 k square is 0. It is a simple quadratic of second order. I can find the roots of this quadratic, which is x 1 and x 2, which will be minus b plus r minus b square minus 4 ac whole by 2 a. Let us do that. So, 5 k m plus or minus root of b square. So, 25 m square k square minus 4 a c. So, 4 2 8 2 16. So, minus 16 m square k square, the whole divided by 2 a. So, that gives me 4 m square. So, which gives me x 1 x 2 after simplification as two k by m and k by 2 m. Okay. There are two roots now. We also know x 1 is omega square. So, omega 1 square can be said as 2 k by m. Therefore, one can find omega 1 as root of 2 k by m, and k value is known, m value if known, one can find omega in radians per second. Okay. Similarly, omega 2 square is k by 2 m. Therefore, omega 2 is going to be root of k by 2 m. So, knowing the values of k and m, one can estimate omega 1 and omega 2 as we have seen. So, we have found out the natural frequencies of the system, but we really do not know which is the lowest frequency or the fundamental frequency. How to identify the fundamental frequency? The fundamental frequency can be identified only by estimating the mode shapes, and then from the mode shape can qualify and find out what is the fundamental frequency. So, the next step is to estimate the mode shape. To estimate the mode shape, the governing equation is simply A x is lambda x, that is A minus lambda x is set to 0, that is k minus omega square m of phi n is 0, where phi n is the corresponding mode shape. Of omega. Okay, let us do that. So, we have 3 k minus omega square 2 m minus k minus k, k minus omega square m multiplied by let us say phi 1, phi 2, set it to 0. That is 3 k minus omega square 2 m of phi 1 minus k phi 2 is 0. That is the first equation I get, minus k phi 1 plus k minus omega square m phi 2 is 0. That is the second equation I have. I want to find the first mode shape. So, what I do is in these two equations substitute omega 1 square as 2 k by m, which we already got. You can see here omega 1 square is 2 k by m. So, substitute that to get the first one. Okay. So, we say 3 k minus 2 m of omega square, that is 2 k by m, okay, of phi 1. I am just substituting the value of the previous equation, minus k phi 2 is 0 minus k phi 1 plus k minus 2 k by m of phi 2 is 0. Simplifying, I get minus k phi 1 minus k phi 2 is 0. If phi 1 is phi 1, phi 2 is minus phi 1. So, the mode shapes corresponding are 1 and minus 1. Since there is a 0 crossing between them, the frequency corresponding to this mode shape cannot be the fundamental frequency, because the fundamental frequency will have no 0 crossing. What do you mean by 0 crossing? Let us try to plot this. I have a system of this type. Okay. You can see here from this figure, this is x 1 and x 2. So, x 1 and x 2. Let us try to plot this. So, this is positive and this is negative, because this is 1, this is 1. So, when you join them, I get 1 0 crossing. Okay. Fundamental frequency cannot have any 0 crossing. It means the omega value corresponding to root of 2 k by m is not the first frequency, but the second frequency, and this is the second mode shape. So, that is why I said just by saying omega 1, it does not mean that it is the first frequency. Fundamental frequency should be qualified based upon the characteristic of the mode shape. So, we found the mode shape, we got the characteristic, there is no 0 crossing, then we can say first frequency. If there is 1 crossing, then second frequency. It means 0 crossing will be of 1 order lesser than the frequency. So, if it is second frequency, 1 0 crossing, third frequency 2 0 crossing, first frequency no 0 crossing. So, we should work out the first frequency. So, as we have substituted omega 1 square as this value, let us do the same logic and substitute for the second value, that is substitute 3 k minus omega square 2 m minus k k minus omega square m of again phi 1 and phi 2, that is the next mode shape, set it to 0, but in this case substitute omega square as k by 2 m. So, 3 k minus k by 2m of 2m of phi 1 minus k phi 2 is 0, which gives me, and the next equation is minus k phi 1 plus k of k by 2m of m of phi 2 is 0. So, simplifying, I get 2 k phi 1 minus k phi 2 is 0 or minus k phi 1 plus k by 2 phi 2 is 0. So, if phi 1 phi 2 is phi 2, then phi 1 is half of phi 2 from this equation. Okay. So, what does it mean is, in a system these are the mass points, phi 1 phi 2 is 1 and this is half. Okay. So, I get the mode shape like this. So, there is no 0 crossing. The corresponding omega now is square root of k by 2m, and this is the first mode shape, which is 0.5 and 1. So, the earlier mode shape was correspondingly 1 and minus 1. So, friends, in this lecture we have started understanding the dynamic analysis of multi-degree freedom systems. We are solving the problem by hand to estimate fundamental characteristics of the system. So, in this example we have used eigensolver method to find omega and phi of a 2-degree freedom system model. We will continue the discussion in the next lecture. Thank you very much.